So that was his doctoral thesis in between all the articles that are earth-shattering and everything. But then he went on. He basically used well, what he found in this thesis, he used that in this next article about Brownian movement and Brownian motion. Brownian motion is basically the movement of particles in a solution. And that wasn't understood before, how that happened. People saw it under the microscopes, they saw particles move in water without non-living particles, basically. Well, I mean, if you see a bacteria, you say, oh, it's alive, it's swimming, but non-living particles. And they didn't understand how that worked, so they had no explanation for that. And he gave an explanation, and basically depended on all the collisions of all the, say, water molecules bumping into this large particle and pushing it in a, well, a bit of random direction. And you see this random direction, and I hope the video starts, but obviously not. So it looks like this. So you see this movement of particles, and some of the particles, they just wobble, or some they move along a line. And he found a quantitative way of basically predicting how far they will travel, depending on the size and all kinds of other variables. And yeah, there you go. All right. So it was controversial because he based his ideas on statistical methods. So of many particles bumping into the large, well, large particle of, I don't know, many more sizes of the molecules, and also kinetic gas theory. So he assumed atoms. He assumed particles, and then went on to explain Brownian motion, and that was pretty controversial. But the first thing he did was link the diffusion coefficient to the temperature. Well, his number of particles, he took 6 times 10 to the 23rd. That was the number that they found in the gas theory, and of course there's pi because, well, if you're talking about spheres, you're going to need pi anytime. And this K is the viscosity and P is the size of the particle. And then he went on and connected this diffusion coefficient, to the length traveled, and this is an x direction, and this is the root of the mean of the square. That's a very standard thing of basically finding an average distance, but in x direction. And then that's just the root of 2 times the diffusion coefficient times the time traveled. And of course, this is only in x direction, and if you do that in 3 dimensions, basically you have Pythagoras in 3 dimensions, you basically multiply by root 3. So you can find the distance traveled in random direction. It's also called a drunken man's path, I think. So if you do random steps in a direction, will get somewhere at some time. You won't stay at the same place. And basically these particles travel in this drunken direction. And he did an example calculation at the end of his article, so a prediction. And well, you can read the German perhaps a bit. But in water of 70 degrees, a large particle, 1 micron particle, so a big particle compared to molecules, will travel approximately 6 micrometers in 1 minute. You can basically, that's a prediction, you can see that happening. You can measure that. So there was a French physicist who did that, Jumper, and he got the Nobel Prize for it. So, so he confirmed that this is in 1926 that he got the Nobel Prize. I don't know exactly when he found this, but pretty soon afterwards. So this was also confirmed. So based on the controversial idea that there are invisible small particles, that sounds almost like magic, but bumping into something. So something that you can't see has a visible effect. And this is the explanation for it.